I haven't looked at the certain fundamental concepts needed in thermodynamics. We just want to look at some calculations to consolidate the theoretical knowledge we had in the previous class. So let's work out some examples. The first one says an astronaut weighs 730 Newton. So remember, we've said Newton, which is or weight. We've said weight is same thing as force. Weight is a force. In Cape Town, where the local acceleration of gravity is that. So we have a G value. What are the astronauts' mass? So we're looking for the mass and the weight on the moon, where G is equal to that. So let's go back to the formula we've been given, which is F equals MA. MA, which is same thing as F, which is same thing as F is equal to mg. Remember, A is same thing as G, our acceleration of gravity. And we know that A is acceleration. So if we substitute that into, if we make m the subject of the formula, we have F over G equals m. So let's use what we've got. We've got the force, 730, and then we've got the acceleration of gravity on Earth, 9.792, and that should give us 74.55 kilogram. That is the mass of the astronaut on Earth. But take note, mass does not vary, because there is no exchange of matter, there is no exchange of material. So the mass of the astronaut anywhere on Earth or any other planet remains the same. I know typically we equate, on a day-to-day basis, we tend to equate weight to mass, but scientifically, there are two different things. Weight depends on the acceleration of gravity, while mass is not dependent on that. So having noted that, let's now go back to our formula. So what would be the weight of this? So we've said it would be this mass of the astronaut on Earth is the same as mass of the astronaut on the moon. That doesn't change. The only thing that will change will be weight. And so we've got that, which is F mg. If we equate that 74.55, multiply that by, we've got the G on the moon, which is 1.67. That should give us 124.5 Newton. So I'm sure many of us have seen on TV and several videos where we see the astronaut floating. They are floating simply because the gravitational pull is so low. The G is 1.67. So based on that, their weight is very low. So they are lighter when they are in the outer space. So that is that. So let's look at another example. Example 2. A block of iron weighs 1.120. Remember, we've said this is also another unit. This is force. This is another unit, equivalent to Newton. This is our force, that is weight. At a location on Earth where the acceleration due to gravity, so we have a G. What would this block weigh on the planet Krypton, where G is equal to that? So we've seen that this varies. We've seen that the acceleration due to gravity might vary, but we were given a formula in the morning where we saw that M equals FGC divided by G. This is a constant. GC is a constant, which is 32.17. So if you plug everything we've got in, we've got our F 1.120 multiplied by the 32.17. So we saw that in the other lecture slides. What is the acceleration due to gravity on Earth? We've got that, we were provided that as well, 32.05. So that should give us 1.124 pound. It is essential to always write the unit it is essential when you're working through your calculations, you show the final unit. Be consistent and show the final unit. So having noted this, and based on what we saw in the previous calculation, we can then go back to say that the force, from this same formula, if we bring it down, we know that F will be equal to mg over gc. So if you just make your F the subject of the formula, we've said that does not vary, 1.124. That's the mass. Mass of the ion, similar as we saw for the astronaut, doesn't vary. We've been given G on krypton, 260. And then we've got we've got GC, which is a constant. And that gives us 9.084 pounds. I think what this is also telling us is, the issues of different, in terms of the gravitational pull, it varies from one planet to the other. So we could see for this particular one that is indicated here, it is higher. So if it's higher, we would expect the weight to be higher. So you could see the weight was lower, the weight of the block was lower on Earth than it is in krypton. So let's move on to example 3. A dead weight gauge with a 1 centimeter diameter piston. So take note of that. D equals 1 centimeter. Every unit provided counts. To measure pressure very accurately, a mass of 6.14, that's for the piston and the pan. So we have M equals 6.14 kg. Brings it into balance. If the total acceleration of gravity, we've got G equals 9.82 meter per second squared. What is the gauge pressure being measured? So we've seen gauge measure being measured if the barometric pressure is 748 torr. If you look at this, all the units so far, everything looks consistent except for this particular one, the barometric pressure. So our barometric pressure is the same as atmospheric pressure. So here we've been given it in 748 torr, which we'll need to convert. Okay, before we move on to the calculation, maybe we should quickly do the conversion. To convert, we want to convert everything. We want so that we can have consistent unit. One torr equals 0.013332. 0.013332, and then that would be in Newton per centimeter squared. So that means if we want to convert that, it becomes 748 multiplied by 0.0013332. That gives us let's just quickly punch that into the calculator to see what that gives us in terms of the atmospheric pressure. So 748 multiplied by 0.0133332. All right, so that gives me, from what I've got here, let me just be sure, 748 times 0.013332. That gives me 9.972 in Newton per centimeter squared. So we've got that somewhere. We've got that. So let's move on. We know. Let's calculate the gauge pressure first. The gauge pressure. We know that F We know that pressure is F over A. Do we have F? No. Do we have A? We can't. We'll derive all those now. But how do we get the F? We know F is mg. And also the area of the piston. Take note, the area of piston is pi d squared. Pi d squared over 4. So that is the area of the piston. So if we put all those things, if we substitute everything in, that will give us 6.14. We've got that here, mass, multiplied by G. We've got that here, 9.82. Right? And then we've got this. If you calculate that, it's going to give us 0. Remember, we've been given the diameter, so it's going to give us 0.785. Let's punch all this into a calculator and see if we are getting things right. 6.14 times 9.82. Okay, 60. This gives me 60.2948. If I divide that by 0.785 divided by 0.785, that gives us, so the pressure of the gauge, this gives us 76.77 Newton per centimeter squared. So that is that. But remember, the question is absolute pressure. Absolute pressure, we've got that also in the slide. Absolute pressure equals atmospheric pressure plus the gauge pressure. So we've got the gauge pressure, 76.77. We've got the atmospheric pressure, 9.9. Remember, we've got that here, so we've got this here. So let's add everything up. So atmospheric pressure, 9.972 plus 76.77. So 9.972 plus 76.77. So that gives us 86.74. And remember, consistency with unit, Newton per centimeter squared. So that's that, Newton per centimeter squared. Let's look at one more example. At 27 degrees C, the reading on a manometer filled with mercury is 60.5 centimeters. The reading, take note of that. Reading of the thermometer on the manometer, manometer 60.5. That would be the height of the mercury inside the manometer, 60.5 centimeter. The local acceleration 9.784, that is G. This is height. G is 9.784. To what pressure does this height of mercury correspond? Another, it's, even though it's not written here, but one of the values you naturally, which you ordinarily be given, will be the density of mercury. And but the question is, what formula? Based on the fact that we have H and we have G, what formula do we use? We learned earlier today that pressure can also be calculated as height multiplied by rho. Rho is density. This is density. Height, and we multiplied by G. So we've got G, we've got height, and then we'll be given the density of mercury, which is 13.53 gram per centimeter cube. So if we plug everything in, we should have Our pressure equals 60, height 60.5. What else? Rho, density 13.53, and then G 9.784. Let's plug that into our calculator. 60.5 times 13.53 times 9.784. That should give us 8. We can just round it up, 8. But what is the unit? What is the unit here? Remember we said unit is always important. Let's just try it out ourselves. So we've said H is in centimeters. 13.53 gram per centimeter cube. And then G, what's the unit we've got for that? Meter per second squared. So if you look at this, we should be left with centimeter cube meter. So our unit for that should be 8G. We've got meter, so we are left with meter per second squared. Remember, minus 2 per second squared, and we're also left with, remember, cm, so we are left with cm raised to power minus 2. So that's our unit. G, meters per second raised to power 2, and per centimeter raised to power 2. All the best. So carefully look through this, and if you have any query, don't hesitate to ask me later on. Cheers.